Hello everybody, this is an attempt to explain proton nuclear magnetic resonance spectroscopy and guide you through the principles and processes involved and eventually lead to an attempt to decipher a spectrum and come up with a structure for molecules into the process. Now, we've already completed work on carbon NMR spectroscopy, and this next stage just goes a couple of stages a little more complicated. So let's get into it and see how we get on. First of all, if we take a look at a particular spectrum, then we will see, for instance, this one. As you can see, this is an NMR proton spectrum of a compound you're going to meet again, and as you can see, it's a little more complicated. We still have the signals, we still have the chemical shift scale, but for proton spectra, the chemical shift scales are a much reduced range from 0 to about 12 parts per million compared to the TMS reference, of course, which is always marked at 0, or we don't always show it. Now, in explanation for the more complicated pattern that we're going to deal with, then let's try and get much more simple. Now, just to remind you, a proton NMR spectrum must be taken in a solvent that does not contain any hydrogen 1, because of course that would give its own signal. So a different solvent called deuterated water or deuterated trichloromethane, for example, where we use a 2H atom instead of 1H, because of course an even mass number will not show up in the spectrum. So we need a D-containing solvent, a deuterium solvent. We still add the TMS, the tetramethylsilane, our reference compound, which contains, as you can see, carbon-silicon bonds, which means that it moves well over to the right-hand side, far right-hand side, and we set the chemical shift scale at 0 parts per million with this, and all the other signals are further to the left, that's downfield from that. As always, we put our sample in a supercooled liquid helium, very powerful magnet, and expose it to radio wave signals. This is sufficient to cause the nucleus, in this case the proton nucleus, to spin against the external magnetic field, and then it relaxes, returning back to its original position with the magnetic field. This is called magnetic resonance. Don't worry too much about that. It's the results of the actual experiment that we always have to deal with. So here is what's called low resolution proton NMR spectrum of the compound that you can see in front of you. This, of course, as you can see, is a very simple ester, and of course we have the methyl group on the right-hand side of this single bond oxygen, and the 3-carbon carboxylic acid side, which gives it, of course, methyl propanoate. Just remember, the methyl bit came from the alcohol, that's on the single oxygen bonded side, and the carbonyl oxygen, that's the C double bond O, comes from the carboxylic acid side. So of course the molecule, if it's an ester, will always have that COO part in the structure. Well, as you can clearly see, this low resolution spectrum only shows 3 peaks. And as you can also see, these are triangular in appearance and lacking some detail. We can, of course, pick out the chemical shift values on the horizontal scale, approximately 1.2, maybe 2.4, and perhaps 3.6. But there's lack of detail on this particular spectrum, and you will not get these. You will instead get the much more detailed, high resolution spectrum. So let's have a look at the same substance under a high resolution instead. Well, of course, the 3 peaks are in the same places on the chemical shift scale, but the detail of the peaks themselves is really quite different. We can clearly see that the peak around about 2 is made up of component parts. If we look from above, we can see that there are in fact three distinct peaks, which we call a triplet. The peak that's centered about 2.2, then you can see this one consists, again, look from above, 1, 2, 3, and 4 sub-peaks. We call this one a quartet. And of course, the single peak at 3.6 is exactly that. It's a singlet. That is just a simple single peak. This multiple pattern that you can see is called peak splitting, and this is something which we will go into later on. Its proper name is spin-spin coupling, and it's basically how the magnetic field of one type of proton influences the magnetic field of others nearby. More about that later. So if we then go into our spectrum and look at some more detail in our process of Proton NMR, we compare it here to the carbon-13 NMR that you've just studied. Well, of course, we can see we deal with the number of peaks. That, of course, reflects the number of different proton environments, like it did the number of different carbon-13 environments. However, there are two additional pieces of analysis for the Proton NMR, which we don't do for the carbon-13. The first of these is known as integration, and this is very simply, we get the computer to measure the area under each peak, and that tells us either directly or relatively the number of protons in each environment, which is a very handy thing when it comes to differentiating between methyl or methylene or aldehyde or different hydrogen groups. The chemical shift scale, as we've seen already, is the same delta scale, but for Proton NMR, it's confined to between about 0 and 12 parts per million, unlike the carbon scale, which of course extends to over 200. The fourth and final part of the analysis that we do for Proton NMR is what we referred to earlier as peak splitting, the fact that peaks sometimes appear singlet or can appear in multiple parts, such as doublets for 2, triplets for 3, and quartets for 4. We also get more complicated splitting patterns of 5 or more sub-peaks. These are referred to nowadays in the exam board as a multiplet. So if it's got more than 4 component parts, it's just referred to as a multiplet. More about that later on. So we're going to look at the analysis of a particular spectrum, which we've just seen for methyl propanoate, and we're going to take apart the 4 different levels of analysis for the Proton NMR. Well, here is our spectrum, and we'll just bear that slide in mind for a moment while we look through it in some detail. As you can see, I've picked out the 4 levels of analysis for Proton NMR, and as you can see, we've color-coded where to find them on the spectrum and what the implications are for them. We'll go through each of these levels of analysis one by one. First of all, as you can see, the 3 distinct separate peaks, and I've shaded them in yellow because obviously you can see that tells us the number of different proton environments, and clearly there are 3 in this compound. Now, different from carbon spectra, we have a number. The number is posted alongside usually the top of the peak or to the side of it, and that number tells us the number of hydrogens in that particular environment. This is called the integration and is essentially measured the area under each peak. And quite clearly, that's really handy when trying to distinguish a CH3 from a CH2 and other groups, of course. More about that soon. The third level of analysis is, of course, the chemical shift scale. And the chemical shift scale for Proton NMR, we more or less center the peak. If it consists of several peaks or components, then try and sort of get the center of that grouping. So we can see there is a a peak centered about 1.2, another one centered about 2.2, and the singlet peak centered about 3.6. The use of the shift patterns is, of course, on your data sheet. Make sure you're using the proton shift patterns, not the carbon ones. And of course, the position of those is measured relative to the TMS reference, which is given the shift value 0. The fourth level of analysis, the splitting pattern, or spin-spin coupling as it's properly known, the splitting pattern is essentially the number of sub-peaks that the major peak is broken down into. And that we'll explain later on in terms of the relationship between the signal we're looking at and the adjacent groups nearby. So those are the 4 levels we're going to do. So let's take these one at a time and make sure we're well versed and practiced in each level of the analysis. First of all, then, the number of peaks. Well, clearly that's very simple because we're familiar with the idea, and I've shaded them in yellow. And you can see on the structure of the molecule, there are also 3 different hydrogen environments. Let's just remind ourselves what that means. The methyl group on the far left of the compound, this one. This methyl group obviously consists of 3 hydrogens bonding to a carbon, which itself is bonding to more hydrocarbon. This particular type of hydrogen is extremely common. As you can imagine, in most organic compounds, these are hydrogens bonding to carbon, and as you can see, a CH3 group is often the end of a molecule. Well, obviously, we can also see that the middle of the 3 peaks on the structure, this CH2 group, this methylene group, is a different environment because the H's on this carbon are obviously bonded on this side to a carbonyl oxygen-carbon group, which of course is different. And if we jump across to the ester group, to the methyl group on the right, you can see, of course, that that is also a methyl group, but is in a different environment because the carbon carrying the hydrogens is single bonded to an oxygen. Again, a different environment. Hence, we get 3 peaks. So we're going to get a bit of practice at working out the number of environments for different molecules. So let's just take a look at the 3 particular environments that our molecule possesses. Now again, we'll deal with these one at a time. So first of all, let's start with the red protons on the structure. That's either these on the left-hand side. These are 3 hydrogens in a methyl group. And of course, every one of the 3 red hydrogens has exactly the same outlook. They are H's bonding to a carbon, which is bonding to a methylene group and 2 other H's. And of course, you can say that about each of the 3 red H's. So this type of H is referred to on your data sheet as a H bonding to carbon bonding to R, where R is other hydrocarbon. These are very common indeed. And of course, you can get them singly, but it's unusual. You do get them in pairs, or you even get them in 3s, or even multiples of 3. So 6 H's in this type would be 2 methyl groups. 9 H's in this type would of course be 3 methyl groups on the same carbon. If we move now to the green CH2 group, I've called these the methylene group hydrogens. And as you can see, the type of hydrogen environment, again from the data sheet at the top here, this is the hydrogen that is bonding to a carbon, which itself bonds to a carbonyl carbon. And of course, if you think carefully, there are plenty of different functional groups and compounds that will contain a groups such as that. We're thinking of things like aldehydes or ketones, carboxylic acids, esters, and all the other derivatives like acid anhydrides and acyl chlorides and amides. So this type of hydrogen environment is quite common and very popular in A-level exam questions. Well, of course, there are 2 methylene H's shaded in green, of course, and as you can see, they are different from the red or blue methyl H's because they're in a different location environment. As you can see, the CH2 group is bordered on one side by the methylene group, by the red methyl group, and is bordered on the other side by the carbonyl group. The final recommendation in blue here, this is also a methyl group, but different, because this time the H and the carbon is bonding not to R, but to a single bonded oxygen. And of course, these sorts of groups are common in esters again, and of course in alcohols. Again, popular with A-level questions. So I've picked on these three groups because they are very, very common, and the different types of H's occur very frequently in exam questions. So we need to get used to recognizing H's on a carbon which is single bonded to O, H on a carbon which is single bonded to a carbonyl group, and of course the straightforward H is on a carbon bonding to more of the carbon skeleton R. Well, here's a little bit of a practice for you. So when you're ready, you can pause the video and have a go at working out the number of different peaks that you'd find in each of these molecules. Look for the different number of environments and write down the number of peaks you would see. Pause. Okay, so hopefully you've managed your attempt to identify the number of peaks in each of these six. And so let's just reveal what the answers should have been. So of course the top one, let's just put them on the screen for you, and you'll see that the A, B, C, D, E, F, when we get there, we'll have got these number of peaks. So first of all, ethanol, the top number, A at the top, as you can see, three different coloured zones, three different peaks, three different environments. B, as you can see, we mentioned this before, there are 9 protons with 3 methyl groups, which are all identical environments. And of course, these are H's on a carbon bonding to more hydrocarbon, and clearly there are 9 of them in these two environments. Don't forget, we've also got an OH hydrogen, which of course is because it's an alcohol. The next molecule, C, as you can see, is a ketone. It's also a symmetrical ketone, pentan-3-one. Remember, we had this issue with carbon-13 NMR. We've only got actually 2 different environments, the 2 methyl groups and the 2 methylene groups. Of course, there's a plane of symmetry. Molecule D, if we look carefully across, then of course we've got this as butanoic acid. And if we count carefully going across, we've got a methyl group, we've got a methylene group, CH2. We've got another methylene group in a different environment because this one is bonding to the carbonyl. And of course, we've got the carboxylic acid group, OH. This is different to the alcohol group, OH. E is also an alcohol, but of course this one is an isomer of butanol, and we've got the number of environments this time is 5. The methyl group furthest from the OH, the methylene group next to that. We've got a solitary hydrogen coloured in blue, which is on the same carbon as the OH. Well, of course, the central carbon that features the H, the methyl, the OH, and the ethyl is, of course, a chiral carbon. And that's not what we're interested in, but just be reminded of that. You can see there are 4 different things bonding to it. We have a methyl group on the far right, which of course is also next to a C with a H and an OH, which is different from the methyl group far left. The last of these compounds, as you can see, is also an ester. And remember, we have a 3-carbon alcohol group side, so that's propyl. And the 2-carbon acid group is, of course, ethanoate. So propyl ethanoate. The methyl group on the left of the carbonyl is 1. The 2 methylene CH2s are different because we've got 1 next to the oxygen. And the other methylene CH2 in green there is, of course, next to a methyl. The methyl on the right is different to the one on the left because of the further distance away from the electronegative carbonyl oxygens and so on. So this is going to be a structure that's going to run and reoccur throughout this video clip. So this is a molecule, it's the amino acid phenylalanine. And if we make a copy of that structure, and we're going to add the information about its analysis down the left-hand side. So we'll pause the video and give you a chance to draw that structure, and first of all, work out the number of different proton environments. And of course, don't forget, there's a benzene ring on there. Okay, so hopefully you've drawn that and you've got a copy of it and you've worked out the number of peaks, number of different environments. We've got the carboxylic acid proton right at the top. We've got the primary amine, the amino group hydrogens on that side. We've got a solitary hydrogen on the alpha, or the 2 carbon and amino acid names. This is this one. The CH2 group, which is part of the amino acid R group, which is a group containing hydrogens attached to an arene ring, which of course contains hydrogens itself. So we've got 1, 2, 3, 4, and don't forget the arene protons, there are 5 of them. That makes 5 different peaks. Okay, so let's move on in our story. Part 2, this is the integration issue. This is the area under the curve, under the peaks. You'll never have to measure that. Nowadays, you're simply given the area that is relative to each peak as a number. And as you can see in our example here, the peaks are listed, as you can see, with 3, 2, and 3 protons respectively. Now, again, if you count up the number of protons in our actual molecule of methyl propanoate, there are, of course, 8 protons, and they are all accounted for by the numbers you can see. So obviously, in the yellow proton environment, there are 3 hydrogens. In the green methylene environment, there are 2. And of course, the other methyl group furthest away from the carbonyls, there are also 3 in that environment. So we've got an additional piece of information which clearly helps us when it comes to working out the structure. The fact that the methyl group has 3 hydrogens tells us it's the end of a molecule. And the yellow methyl group on the right-hand side is also the end of a molecule. The fact that we've got a CH2 means that there must be something bonded either side of it to make up the 4 bonds. Now, obviously, the number of protons could be given to us, as indeed it usually is, in the same form as just a number. But in the old days, the information on the integration used to be given in what the form of a step height trace, which looks like this. Same molecule, and the spectrum displays the same 3 peaks, but this time the information was plotted by computer as a step height trace in red, as you can see. And all that we had to do was measure the vertical heights between the intervals. And if we measured the vertical height in millimeters, say, then the first vertical height was 12, the second vertical height is 8, and the third vertical height is 12 again. Now, of course, making this the simplest ratio allows us to give the numbers 3, 2, and 3. If you think about it, dividing by 4. So 3, 2, and 3 is, of course, what we would be given nowadays, the numbers in blue, but they used to be illustrated as an integration trace, and we measured the vertical height. We don't do that any longer because, to be honest, students and using their rulers accurately is not something that goes down terribly well in exams. Okay, so here are some further examples. It's the same molecules which we used before. We've got the shaded number of peaks, as you can see. Now, what I want you to do this time is I want you to write down the number of protons in each environment, and we can write them down as a ratio, for example. So, for instance, the ethanol peak, which is molecule A, yes, we've got 3 peaks, and the ratios of their areas, the integration values, will of course be 3 to 2 to 1. So we want you to do pause the video while you work out the ratios for the other 5 molecules. Okay, so hopefully you've managed to do that, and we'll just take you to the next slide just to see if you did get those ratios correctly. Okay, so B, of course, 9 to 1. That's 9 of the methyl protons to 1 in the OH group proton. Our pentanthreone, molecule C, well, of course, the number of actual protons is 6 in the methyl type and 4 in the methylene group. Well, of course, this ratio simplifies to just 3 to 2. Molecule D, again, 3 methyl, 2 methylene adjacent to carbonyl, and the carboxylic acid H is, of course, 1. Molecule E, a little more complicated, 3 methyl H's, a methylene 2 H's, a solitary H on our chiral carbon, a solitary alcohol H, and of course a methyl group, again 3 H's. And finally F, our molecule, of course, ester, which was propyl ethanoate, the methyl group next to the carbonyl, 3 hydrogens, the methylene group next to the single oxygen, CH2 group, that's 2, the green methylene group next to the terminal CH3 is also 2, and of course the final methyl group furthest away from the oxygen is also 3 protons. Back to our phenylalanine, and of course, having worked out that we had 5 peaks from 5 different environments, what I want you to do now is work out the integration values for the 5 peaks from the structure you see in front of you. I'll pause the video and you can fill in the ratio for those peaks. Okay. The third level of analysis to come on to now is the chemical shift scale, which we are familiar with from the carbon NMR, but of course this time the chemical shift scale is referring to protons, and the shift values are much lower, remember, between about 0 and 11 or 12. Now, remember, the same principle applies as applied to the carbon spectrum, and this is the upfield downfield principle. The closer your protons are to an electronegative atom, the further downfield, that's to the left, at a higher shift value, you'll find them. Now, also, similarly, the further away your protons are from any electronegative atoms, the further to the right or upfield they will appear, closer to TMS. So bear that in mind if you've got 2 peaks in the same zone or region. We can often tell which is which by the proximity to electronegative atoms. Well, of course, the chemical shift values for a grouped peak, as you can see, then we tend to aim for the middle of that group, or you can give a range, it's up to you. But I've picked out in red at the top here, we've got a peak, let's say, centered at 1.2. which is the 3 hydrogens in the triplet furthest to the right, closest to TMS. We've got the 2 hydrogens, which as you can see are in a 4-part quartet, which is of course at 2.3, and the solitary or singlet hydrogen, which is occurring at about 3.7 on our delta shift scale. Now, of course, this requires us to consult and use the data sheet and to quote these shift values. Just the same as you would do with an infrared spectrum, you can't just label it C double bond O without giving the wave number range. Same with this. If you're going to quote chemical shift values, you must get them from the data sheet and quote them in your answer. Well, of course, as you can see, everything is measured relative to our reference TMS, which we don't usually get shown on exam questions, but they do ask you, what is it, why is it used, and what's the point of it as a reference, of course. So here is our data sheet, and of course this is with you in all the exams, so let's just have a little look as a guide for you. Roughly speaking, furthest to the right at the lowest shift values, we will find hydrogens bonding to carbon, joined to just other hydrocarbons. These are very, very common indeed, as these are sort of the fundamental parts of an organic compound. When we move to the left, higher shift values, roughly in the region 2 to 3, then we tend to find 3 particular environments, and any of the 3 of them could be anywhere in those regions. Well, of course, the H is on a carbon, which is basically a side group on a benzene ring, which, as you can see, is between 2 and 3. One of our most popular groups, which of course is H on a carbon bonding to a carbonyl, very popular, remember, that's in this region as well, and a hydrogen on a carbon that bonds singly to a nitrogen, very uncommon in exam questions. When we go further downfield, that's to the left of course, we have a hydrogen on a carbon which is single bonded to an electronegative atom. Again, H on a carbon single bonded to O will occur somewhere between 3 and about 4.4. They tend to be quite far to the left of that zone. We also have hydrogens bonding to carbons with chlorine or with bromine. Again, not very common in exam questions, the last 2. Further, again, downfield between about 4.5 and 6, we have alkene protons. These are H's on a carbon double bonded to another carbon, and this is a genuine alkene proton that you'd find in molecules like ethene and propene and so on, and phenylethene. Well, here we move along further downfield again, so somewhere between about 6 and 8. They tend to be centered around about 7.3, these things. These are arene protons. And of course, the illustration here is showing you a hydrogen that's directly bonding to a benzene carbon. And of course, if you had just benzene, then you'd have 6 of these arene H's. What's very revealing and very interesting, of course, is if we have 5 arene H's on a molecule, then that means something very important. We have a mono-substituted arene, where the 5 remaining protons are still attached to their carbons, but the 6th one has been substituted. Something, for example, like nitrobenzene or methylbenzene would be different, with only 5 arene H's. 4 arene H's would mean a di-substituted arene. That's 2 groups replacing hydrogens on the benzene ring and so on. And of course, if you think about something, for example, like 2,4,6 tribromophenol, which has had the 3 bromines and the phenol OH group replacing 4 of the H's off the arene, that would only have 2 remaining arene H's. So do watch out for that, because it is quite handy when working out structures. The aldehyde proton is really quite close to a carbonyl group, and of course is right down the spectrum here between about 9 and 10. The carboxylic acid proton, again, down somewhere between 10 and 12. These are pretty often recognizable as just single peaks, and that they are downfield further to the left of all the others. Now, there is one particular peak that we do need to discern and understand a little more. These are hydrogens not bonding to carbon directly, but bonding to electronegative atoms themselves, such as OH or NH. And as you can see by the width of the shaded band, how useless is this? Anywhere from about 1 to 12 is where we might find these. And of course, that could be an absolute nightmare. A peak appearing anywhere in that region would be rather difficult to decide. Well, there is something we can do about that. We can make these disappear. More about that later on. But as you can see, the OH or NH peaks will be quite obvious. They're only ever single. They don't split ever. And they are reasonably small and can be fairly simple and represented quite obviously when you see them. But we have a way of finding out where they are by running two spectra, which you'll see later on in this presentation. So there's your data sheet. Very simply, the further to the right you are, then of course the more hydrocarbony you are. The further to the left, the more you've got the very electronegative groups around you, and the sort of polarized bonds somewhere in the middle. Okay, so there's the basic outline of the data sheet, but of course you must quote the values of the bands or zones when you refer to the shift values. So picking out our particular molecule again, this is our same spectrum of methyl propanoate again for the next appearance. And as you can see, we've illustrated the three zones by picking out the centered peaks about 1.2. And again, looking at your data sheet, a peak at 1.2 must correspond to hydrogen bonding to carbon, bonding to more hydrocarbon. And these, of course, are going to be found around about 1 to 2 on the data sheet. As you can see, very obviously, that triplet, that three peaks, is the three hydrogens in that methyl group at the structure at the at the left-hand end, which of course is part of our ester compound. The signal, that's a four-part quartet, as you can see, which is centered around about 2.3, is one of those three groupings. Well, of course, we know our molecule is an ester, and of course it is not an arene, and it doesn't contain any nitrogen. So instead of worrying about which one it is, and of course it can only be one of them, and that of course is hydrogen on a carbon bonding to a C double bond O group. Very common indeed, and watch out for it. Don't confuse that with arene groups with carbons with hydrogens on them. That's also a very common mistake to get those two mixed up. Further downfield, of course, really close to the electronegative atom, then we've got hydrogen on a carbon single bonding to O. Well, of course, that's again what we'd find in an ester, and that's the location. And you may be wondering, well, we can see where it is and we know the type of proton it is, but let's have a think about why we have this much less complicated signal for that one compared to the others further upfield. Okay. All right, so if we examine our regions again and look at them on our molecule, then this is an interesting issue. So in the box I've picked out, this is the signal that we're going to pick up between 3 and 4, 3.7, and this corresponds to hydrogens bonding to carbon, which is single bonded to an oxygen. And as you can see, picked out on the structure. And those are very close to the oxygen. In fact, anything within 3 bonds is under the influence of the oxygen. If something is 4 or more bonds away, then the influence doesn't really get that far, and you can sort of ignore any effect. But 3 bonds or less, then it's a direct influence on the actual signal that we'll get. So I've drawn in the blue box there. This group is 3 H's in that environment. So not just one, there are 3 hydrogens. So let's just put a CH3 group instead on the oxygen. So that has taught us to have 3 H's of that same type is of course a methyl group on the single bonded oxygen. The methylene group on this next picture is showing us that must be 2 hydrogens of that type, H's on a carbon bonding to carbonyl carbon, and clearly if there are 2 of them, then they're on a CH2 group next to the carbonyl carbon. And of course this is centered between 2 and 3 on the shift scale, and that is also what we'd expect to find in our ester, very common peak. Clearly there's no nitrogen in our compound, and obviously it's not an arene, so we could ignore those other 2 potential bonds and potential groups. Finally, and very commonly, is the peak furthest to the right at the lowest shift value, right next to TMS if you like, and this of course is a very common methyl group. These are hydrogens on a carbon bonding to more hydrocarbon. We represent that by R, of course. And there are 3 protons in this environment. That, of course, is the end of the molecule on the left-hand side. You may be wondering why this is at the lowest shift value compared to the other methyl group. Well, of course, simply it's further away from the oxygens. It's the furthest proton environment from either of the oxygens, which is why it's furthest to the right on our data sheet, and of course has the lowest shift value. Okay, so back to our phenylalanine, and this time what we want you to do is to work out or write down the identity of each of the proton environments that we're looking at, and state the chemical shift value approximately of where we might find them on the chemical shift scale. So we want the type of proton, so is it a H on a carboxylic acid? Is it a H on a carbon on a benzene ring? Is it an arene H? Is it an NH proton? Whatever. And where would we find it on the chemical shift scale? And of course, you're going to have a problem with the NH2 because, as you saw on the data sheet, it could be, well, just about anywhere, really. So pause the video and have a go at doing this bit of the analysis. Okay, so we'll move on after our phenylalanine. We'll come back to this molecule later on because, of course, we've still got one level of analysis to get through. And this, of course, is the one we've not seen before. And this is the splitting pattern, or spin-spin coupling as it's referred to. Now, we've got to be very careful about how we understand and explain this, because what we're looking at is a peak which in some cases is split into lots of other parts. The table underneath shows exactly what I mean, and the actual wording that we use to describe the multiple peaks and the significance of the actual number of peaks that we get split. So first of all, in the table, a singlet is a peak which is not split at all. Then we have a doublet, which is a peak that's split into 2 of equal height, as you can see. The triplet, which we've seen already, is 3 peaks. They're actually in a ratio of 1 to 2 to 1. And a quartet we've seen already on our spectrum, you can see above there. We've got 4 peaks. These are in a ratio of 1 to 3 to 3 to 1. And we go beyond 4 peaks, we have a thing which referred to, you could use the old name, which is a pentet for 5 or a sextet for 6, but we now use the catch-all term, if you like, multiplet, which is for 4 peaks or 5 peaks or more. Okay, so as you can see, there are 5 peaks in this bundle, as you can see, and those are in actually a 1 to 4 to 6 to 4 to 1 ratio. Now, the important point here is not to be lost on you. The signal that we're looking at is influenced by the neighboring or adjacent protons. These are hydrogens on the carbon next door. So when we're looking at a signal for a particular hydrogen environment, we get some information from the splitting pattern, which tells us actually the number of H's on the carbon next to it. Now, the table column 3 here, which as you can see, a singlet has no H's on the adjacent carbon, or it might not even be a carbon. A doublet has 1 adjacent H. A triplet has 2 adjacent H's. They could be on one side or either side. A quartet will have 3 adjacent H's. And of course, a triplet and a quartet are what we have in our spectrum, and these are very common. A triplet and a quartet usually shows us an ethyl group. More about those recognizable ones later on. The multiplet, which we don't have on our spectrum, is of course far more complicated, and that will have 4 or more adjacent H's. So there's actually a very simple relationship between the splitting value, that singlet, doublet, triplet, quartet, and the number of adjacent H's. And of course, this is worked out and referred to as the N+1 rule. So the number of adjacent H's plus 1 tells us the splitting pattern doublet. The number of adjacent H's 2 plus 1 gives us a triplet. The number of adjacent H's is 3. We get 3 plus 1, a quartet of peaks. And of course, 4 or more adjacent H's, we get the 5 peak pentet, or example of multiplet. So the signal that we appear to identify, be careful, is under the influence of what is next to it. More about that now. So what I've done here, just to try and firm that understanding up a little bit for you, is I've put the protons whose signal we are looking at in a red box, and I've shaded in green the adjacent protons. So let's have a little look at our methyl group here on the top left. And of course, there are 3 protons in that environment. So what happens to its signal? Well, if we look to the right of it, there are 2 in green adjacent H's. Plus 1 will give us a triplet. So the signal for our methyl group will appear as a triplet and is furthest upfield, closest to TMS. And of course, that's the triplet you can see here. Why is it a triplet? Because there are 2 adjacent H's next to it. If we move down to look at our methylene group, and of course from the spectrum, we can see it's a quartet. Why? Well, of course, if we look to the left of our methylene group in the green box, there are 3 protons. Plus 1 makes a quartet. On the other side is a carbonyl carbon. It has no hydrogen, so it makes no contribution to our total. So you add up the number of adjacent H's on either side, on the carbons immediately to the either side, add them together and plus 1. So we've got 3 and none, plus 1 gives us a quartet. And then finally, if we look at our methyl group on the right here, then as you can see, there are 3 protons in that environment, but next to it is an oxygen. That's not a carbon with hydrogens on it. It's nothing in the adjacent environment, no adjacent H's. Plus 1 is, of course, why we get a singlet peak for the methyl group on the single oxygen. So that's the origins of the splitting pattern, and it tells us directly what's next to the group we're actually looking at. So do please bear that in mind. The N+1 rule, the number of splits that you get, number of subpeaks you get, is telling us the number of adjacent hydrogens, and of course plus 1. So a quartet, work backwards, will have 3 adjacent protons. A triplet will have 2 adjacent protons, so do be careful. Okay, and I mentioned this before, of course, the proximity and that 4-bond rule is still in there. So if you're thinking about how far away a proton has to be to influence the signal of another, then there's the answer. The N+1 rule works as long as the protons that are considering being splitting are no more than 3 bonds away. So if we look at the top picture, we can see that in our molecule, the CH3 group, which is picked out in red, there are no H's on the oxygen, and of course there are no H's on the carbonyl carbon. So there will be no splitting, and that is why that is a singlet peak. The protons in the orange ring circled up beyond the carbonyl group, those are 4 bonds or more away. They will not influence the signal for our methyl group. Whereas if we look further down, of course, we have in red the 3 methyl protons, which will be influenced by the methylene group next to them, which is why they will cause splitting of the methyl signal in, of course, 2+1, which makes a triplet for it. Similarly, the methylene group of 2 protons has a methyl group to the left of it, and so its signal will be influenced and split, and of course will be split into 3+1, That's the number of adjacent H's plus 1, which of course is a quartet. Right, so just a little further detail. Now, you're not going to be asked this, it's just to help you understand the ratios that we mentioned. And if we just look carefully at this very simple molecule, this is ethanal, and of course that's a very simple aldehyde. We have two recognizable environments, as you can see, the aldehyde hydrogen and the methyl group hydrogens. Again, on the spectrum, where we'd expect to find them, the aldehyde hydrogen is down around 9.7 on the shift scale, and the methyl hydrogens are, of course, close to, remember, these are H's on a carbon bonding to a C double bond O. So these are not your methyl group on a hydrocarbon connection. These are H on a carbon bonding to CO double. And that is, remember, between 2 and 3 on the shift scale. Use your data sheet. Well, of course, that signal is now a doublet. That's 2 peaks. So let's just explain how this arises. First of all, let's look at the methyl signal and the methyl group signal, the doublet. Why has that happened? Very simply, our adjacent H, which is on the carbonyl group, the aldehyde carbon, then that H could be either with the magnetic field or it could align itself against the magnetic field. So the signal for the methyl group is influenced by a H on the aldehyde, which is either with or against it. That's going to give 2 signals or a split signal into 2 parts. Now on the left-hand side, a little more complicated, the aldehyde proton itself. Well, of course, on the carbon to the right of that, the methyl group, there are 3 H's, and they are within 3 bonds, so they will affect the aldehyde signal. And of course, the aldehyde signal will be split into the number of adjacent H's is 3 plus 1 is 4. The aldehyde signal down at 9.7 appears as a quartet. Now, the ratio of those peaks we said was 1 to 3 to 3 to 1. It's a bit complicated, this, and they'll never ask you this, but here's why. Those arrangements for the 3 methyl protons. So if we look at the arrangements, and I've used the up and down arrows to show the possible arrangements for these, then they could all 3 of them be against the field or with the field. And of course, we can have 2 up and 1 down and 2 up. I've used up and down as opposed to with or against, but you know what I mean. So we've got 3 down, we've got 2 down and 1 up, 1 down and 2 up, or 3 up. Well, of course, there are 3 different versions of 2 down and 1 up, just by looking at the arrows. And there are 3 different versions of 2 up and 1 down, which is why we have 1 to 3 to 3 to 1 ratio. This is an ethyl group, again, a very common structural feature, and this also a very common pattern. We have a quartet and we have a triplet. Well, of course, the ethyl group, the CH2 part of it, will be obviously split into a quartet because there's a methyl group next to it, 3 hydrogens plus 1. The ethyl group itself on the right, there are 2 adjacent methylene protons plus 1, means we'll get a triplet. And again, I've aligned the atoms, the protons, so you can see whether they are with or against the field. We've already seen the 1 to 3 to 3 to 1 option for the methyl group part of the molecule. Well, let's have a little look now at the methyl group itself and the effect of the methylene. Well, of course, there are only 2 methylene protons, and they can both be against the field or both with the field, or of course 1 up and 1 down, or 1 down and 1 up. This is a ratio of 1 to 2 to 1. So those of you who study maths and may have come across something that gives you all of these ratios is a thing called Pascal's triangle. And it tells us the relative ratios of these peak heights. So a singlet, of course, is 1, a doublet is 1, 1, A triplet is 1 to 2 to 1, and a quartet is 1 to 3 to 3 to 1. And the next row of the triangle would, of course, be 1, 4, 6, 4, 1 for the pentet. Okay, so here is an example for you to try the n+1 rule. So what I want you to do again is pause the video and have a go at these four. The idea, of course, is the signal of the protons in the red box is the one you're working on. So look at the number of green adjacent hydrogens and work out what the splitting pattern, refer to it by the number of peaks and the splitting pattern word like doublet or triplet and so on. Okay, so I'm going to pause the video and let's see how you get on with analysing these. Now, at the bottom I've shown you in blue or purple, then those protons are too far away. Remember, they are more than 4 bonds away, so they have no effect on the immediate signal of what's either side. So just count up the number of green protons effectively and add 1. Okay, well, I hope you managed to decipher those. The signal for the top left-hand side methyl group will, of course, be split into a triplet because there are 2 adjacent protons +1. Top right, the signal here will be split, of course, into 3 and 2 is 5 and 1 is 6. So that is what's called a sextet or a multiplet because, of course, there are 5 adjacent protons +1. The methylene group on our compound, as you can see, which will be split into, add them up, 2 on one side, 1 on the aldehyde group is 3, plus 1 makes, of course, 4. So this will be a quartet, and of course there are 3 adjacent protons plus 1. And then finally, the aldehyde group on the far right-hand side, then we can see that that solitary aldehyde hydrogen is only influenced by the immediate methylene group to the left of it. So that will be split into a triplet because there are 2 adjacent protons plus 1. Okay. So here's another one for you to try. We're going to pause the video, and this is an exercise for you. So the box in red is the one you're looking at, and count up the number of adjacent protons plus 1 to tell you what the splitting pattern is going to be. Okay, we got butan-2-ol first, so let's work our way across it. The methyl group on the far left, this one will be split into a doublet, 2, because there is just 1 adjacent hydrogen on a carbon. The hydrogen on the OH group is too far away and doesn't split, and we don't do that. The solitary hydrogen that's on carbon number 2, then of course there are 3 methyl group protons on the left of it and 2 methylene protons on the right of it. So that will be split into 3 plus 2 plus 1, 6, a sextet or multiplet. The OH group itself, as a rule, is never split, okay, because it's bonding to a hydrogen, bonding to an oxygen, and not a carbon. And that is only ever a singlet peak. OHs are only ever singlets. The methylene group next to that, CH2, well, of course, be careful. There's a methyl group on one side, so that's 3, and there is a solitary H on carbon 2 as well. So add those, that's 3 and 1 is 4. And of course, plus 1 means that will be 5 peaks, or a pentet, if you want to call it that, or multiplet for the methylene group. Finally, the methyl group on the far right, there are 2 adjacent protons, and of course, plus 1 means we get a triplet. Over to butan-1-ol, and of course, we had problems in identifying from carbon NMR spectrum the butan-2-ol or butan-1-ol. From carbon NMR, we got 4 peaks, but we weren't quite sure about where they were or the sort of spread of these 4 peaks. Well, the proton NMR spectrum will, of course, be very, very different and very much more diagnostic. First of all, the methyl group on the left, as you can see, has 2 adjacent protons, so that will be a triplet up here. And the methylene group is right in the middle, so watch carefully. There are 3 methyl protons on the left of it, and there are 2 other methylene protons on the right of it. So 3 and 2, of course, is 5, and 1 is 6, so you can call it a sextet or multiplet. The methylene group, next one along, there are two methylene hydrogens on the left, and there are two methylene hydrogens on the right of it. And so, of course, that will be 4 plus 1 is 5, a pentet or multiplet. The last CH2 group before the OH, well, of course, there are two adjacent CH2 protons. We don't count the OH proton because it's not on a carbon. So that will be 2 just plus 1 is a 3, so that's a triplet for the methylene. And finally, the alcohol OH group, of course, is only ever singlet. So the splitting pattern for that is really quite different. Okay. So just to remind you of some of these very common splitting patterns and what they actually tell us. So we've already seen triplet and quartet top right there, which is significant because we often get an ethyl group. It also shows us the end of the molecule where we've got a terminal methyl next to a CH2 group. Two triplets together we'll find in the middle of a molecule, or certainly not at the end, because that represents two methylene groups. For example, a chain of hydrocarbon, let's say butane, would have a CH2 in the middle of it, which would show up triplet. We do get some unusual combinations. A doublet and a quartet, if you think about it, is obviously a CH3 next to a carbon with a solitary H on it. The solitary H signal is split into 4 because there's 3 adjacent protons plus 1. The methyl group signal is split into 2 because of the adjacent H plus 1. And then we get a rather interesting thing here. We've got here a doublet and a multiplet. This is a carbon with a branch on it, a methyl group, and of course the end of the molecule with 2 methyl groups. Those 2 CH3 groups will of course be an equivalent environment of 6 protons, and they will obviously cause a splitting effect. And this is what happens. The solitary H on the carbon will be split into a multiplet, which is lots of peaks, of course. You won't be able to count them, there's so many together. And of course, the methyl group's signal will be split into a doublet because of the solitary H on their shared carbon. Now just remember, OH groups or NH groups are only ever occur as a singlet peak. They're usually quite short, stumpy looking things like you can see in the pictures. They don't have any splitting. Again, I did point out that if you've got 5 arene peaks, then you've got a monosubstitution, 4 arene peaks, disubstituted benzene. I'm pleased to tell you, you will not be expected to analyse or explain any splitting of arene peaks whatsoever. Just the fact that there are 5 or 4 or 3 arene H's present. So don't worry about splitting patterns for arene peaks. They will not be asked of you. Now, what do we do about OH and NH? And of course, the OH and NH peak is very variable. And as you see on the data sheet, it could be from anywhere on the actual spectrum. These protons have a very wide chemical shift value and are very difficult to locate. They are only ever singlet peaks and they never split. So what you do is you look for a singlet peak. Well, of course, what happens if your spectrum already has a singlet peak? You'll have 2 of them or more. So this is what we do. We go through a double spectrum process, and the first one is a normal spectrum. We run a spectrum as normal, and as you can see from the top image, we've got 1, 2, 3, 4, 5 peaks. It does feature 2 singlets, one of which is our OH group, but where the devil is it? So what we do next is we treat the sample with deuterium oxide. This is heavy water, D2O. Remember, we use D because it doesn't have a signal unlike ordinary H does, and because it's got an even mass number, of course. So when we add D2O to a sample, then the protons in equilibrium exchange with the genuine H's that are on the molecule. So the OH or NH, which are called labile protons, means that they can be swapped. in which case some of them will, instead of being H's, will be D's instead. So if you look at the ethanol example underneath, the ethanol equation reacts with D2O to replace the hydrogen on the oxygen with a D. Now this only happens on OH or NH because of the serious polarization of that OH or NH bond. It means that the hydrogen is much easier to come off and be replaced by a D than an ordinary hydrocarbon hydrogen that's bonding to C. So because of the OH or NH, we replace the H's with D, and we get this different version of ethanol with a proton which is now covered up, masked, hidden, or is now no longer going to be visible. When we run the spectrum again and compare them, well, of course, one of our peaks is missing. The peak that disappears is, of course, the OH or NH peak, which has now been replaced with a D. So it won't give us a signal. So all we do is we look for a second spectrum run with D2O and look for the missing peak, and that was our OH or NH peak. So that is called proton exchange, and we use deuterium oxide because, of course, it doesn't give us a signal. Finally, on this part of it, then here is our phenylalanine that we kept coming back to, and we've got the peaks, as you can see. I've shaded them color-wise, we can see them, and we've also recorded their integration values. There's one carboxylic acid proton, there are two amino protons in yellow, one H on the carbon in green, there are two H's on the carbon side group of the benzene ring, that's in blue, and the arene protons themselves, of course, is a monosubstituted arene. Then there are 5 of those in that particular environment. The shift and type of protons is helpful from the data sheet. As you can see, the COOH peak will occur somewhere right down at the end between 10 and 12. Amino H's, which of course are one of these variable groups that we wouldn't be able to identify without proton deuterium exchanging. NH's anywhere between 0.6 and 12. The hydrogen on a carbonyl group, of course, very common, between 2 and 3 on the shift scale, and the hydrogens on a carbon bonding to a benzene ring in the same zone between 2 and 3. And then, of course, the arene protons themselves, somewhere around about 7, which are a multiplet, but don't worry about that because we don't deal with the splitting of those. The final part of an NMR proton analysis is often the most tricky bit. This is taking the pieces that we've identified and putting the jigsaw back together. Well, we know we've got an arene ring with 5 H's on it, which is therefore monosubstituted. We know we've got 2 arene H's on a carbon group coming off the ring, because that is our blue peak. So we've got a CH2 group on our benzene ring. Further on from that, we also have, we know, 2 H's on a carbon, which is also bonded to the benzene ring. So beyond that, we find we have a single H on a carbon bonding to a C double bond O group, just one of them. And that, of course, is our green shaded solitary H on the second carbon. Our amino H's, there are 2 of them, so that's an NH2 group. And of course, the solitary carboxylic acid proton furthest to the left on the spectrum is, of course, a carboxylic acid group. So it becomes quite tricky sometimes to basically assemble all of those bits together to produce a structure that everything fits. This is where the splitting pattern helps us, because obviously singlets are clearly the carboxylic acid and the amino group, but the triplet and the doublet help us a lot. The triplet, of course, is because the signal for that solitary H has 2 adjacent H's on the CH2 next to it. So that tells us the CH2 must be next to the C with the H and the carbonyl group. Similarly, the doublet splitting pattern, of course, is because the two H's on the carbon from the benzene ring, then there is a solitary blue H next to, adjacent to that, so that signal will be a doublet because of those. Well, of course, there couldn't be anywhere else to put the COOH group or the NH2 group than the two remaining positions on that same carbon.